true. Think about what happens, for example, when you have a metal bar just resting on the fire. As it starts to get hotter, it begins to glow, initially just red, and then all the other frequencies begin to kick in. So it goes from red through blue to white heat. But no matter how hot it gets, it's never going to explode. This was a prediction from Maxwell's theory that completely failed. The infallible Maxwell had made a mistake. It was a body blow to physics. As Planck tried to untangle what was going on here, he came up with an idea that was completely counterintuitive. Now, because Maxwell thought light was a wave, he reckoned that when bodies get hotter and hotter, there's absolutely no reason why they shouldn't emit more and more light. Planck then came up with a really cunning scheme to try and make the theory fit the data. Planck's problem was similar to the one Thomson had faced. Thomson had had to decide whether cathode rays were waves or particles. Planck faced an identical dilemma and came up with an extraordinary solution. What Max Planck was saying, and for him it was a quick technical fix, was that sometimes light seems to be behaving like a wave, but sometimes it seems to be behaving a bit like a particle. Now, after a bit, it quickly emerges that that's a really revolutionary idea. It completely undermines the basis of modern physics, because light turns out to have a split personality. Suddenly, young physicists had a big, new, world-shattering problem to work on, and they'd staked their careers on trying to understand light's schizophrenia. Everything in physics that had been taken for granted was now up for grabs, and every ambitious young physicist wanted a piece of the action.
The abstract atomic physics developing at present will one day fit more harmoniously into the great edifice of science.
It turned into one of the most exciting and creative periods in the history of science. Quantum physics was born.
Anyone who is not shocked by quantum theory has not understood it.
Planck's revolutionary explanation of light forced a fundamental rethink of the basic properties of matter.
The area of scientific knowledge has been enormously extended, and theoretical knowledge has become vastly more profound in every department of science.
And what began to emerge was a whole new world of tiny subatomic particles no one until now had ever imagined could exist. To Thomson's discovery of the electron were added new particles like neutrons and protons. The scientists even wrote songs to get the public interested.
Protons are creaking and chattering, electrons are rolling and clattering, light comes rushing with a wince. All this nonsense makes no sense, no, no.
The excitement eventually resulted in a completely different picture of what the atom is like. It's like a planetary system. There's a central nucleus stuffed with neutrons and protons, and around that nucleus orbit the negatively charged electrons. But what really mattered was that this atom was bubbling with energy. The atom itself could be an inexhaustible source of power. A new physics was born, a physics of the atomic age. Atomic physics gave us nuclear fission, a terrifying new power was born. Out of the ashes emerges a completely different, completely new vision of what light really is like. And it's a very surprising one, because it's a vision of uncertainty, not at all a mechanical world in which effects follow causes in a rigorous chain of consequences. This is the worldview of modern quantum mechanics, a worldview in which light shifts its character between wave and particle. It has completely changed the way we think about light, and it's completely changed the way we think about the world. Ironically, the more we've uncovered its mysteries, the greater those mysteries have grown.